and start with 5 alpha. So module 5 alpha, identify basic facts concerning digital communications theory. You have to get 70% or more on the test in order to get through it. It's actually a module test now. AFSC application, when it comes to our digital communication, we are dealing with everything from computers all the way up to radios. We are getting to the point where we are linking all of the computers with the radios and being able to make good communications happen with it. You're going to see when we get into the ROIP, which is Radio over Internet Protocol. It's coming. So we're going to look at digital communications, the necessity of digitization, elements of digital comm terms, types of multiplexing. Let's get right to it. What is the necessity of digitization? Well, the big thing is you're converting analog to digital, and by using digital and being able to modulate with it, you're not as much susceptible to the noise. It's easier to pull ones and zeros off of a modulated signal than it is to pull an analog signal without too much of interference in it. There is what we call the elements of digital comm. You can see there's a chart here. It goes from the source, the input, transducer, the analog to digital converter. You got a source encoder, a channel encoder, a digital modulator, and a digital to analog converter. What does that mean? Well, if you took this, I can think of one thing right now. It's called a modem when we're dealing with our computers, sending it to the distance, or you can literally put this in a radio. So it has many uses. The big thing is with the modem, it's considered a full duplex just as well as a transceiver can be classified as a full duplex, but depending on the situations. With the modem, everybody thinks it's full duplex, but it does work off of time such as our phase lock loop, being able to sync everything up down the line through our modems to servers to our nodes, whatever you want to classify them. The whole thing is based off of time. Timing is everything. If you're not in sync, wow, it kind of reminds you of the boy band, doesn't it? If you're not having a synced up operation, you're going to be out of time and things are just not going to work until you get things back in. So we have several different things here. I've pulled this particular chart right here and started working on making it clear. This is the transmit side, the channel being, hey, I'm sending it out. So the transmit works as source converts the analog to digital. You're going to be using probably PCM, some sort of PCM with it. And then you're going to take that source encoder and it's going to take all these ones and zeros and see if it can't convert them into a lesser being. The encoder adds the correction bits. That one is a whole can of worms that you can open up. But when it all comes down to it, when you combine your signal formats from your source, let's just say that you are dealing with computers, you're converting that digital into digital, so to speak. The source encoder is sitting there going, let's see if we can't scale this back a little bit. And then you're going to add what's called correction bits. I call it the Wheel of Fortune. At the end where the contestant is, gets to call out a few letters after host gives them a few letters. So why is that? Because when you put it all together at the distant end, you'll be able to make a 8-bit word out of it. The digital modulator, That one is converting all that digital information, putting it on an analog signal. Because when you think about it, analog goes farther than digital. Haven't quite got to the point where you can transmit digital at a great distance. Let me take a look at, what was it? Edison, and who was the one that did the Van de Graaff? Anyway, there's a History Channel about it. He had DC, the other guy had AC.
Tesla.
Thank you, Tesla. And it pretty much worked out in the end that AC was was more cost effective to get from point A to point B than digital. Digital, you needed, or I should say, direct current needed a bigger cabling system, beefier cables to send it from point A to point B. So it was very cost prohibitive to have it run in. That's the transmit side. This is the receive side. Basically, everything that you know about transmit, just backwards compatible, and that's your receive. So anything that you did in transmit, it's the opposite. So transmit's modulation, receive is demodulate. But in the wonderful world of digital comm, it's uh, multiplex or demultiplex is another set of words that you might hear out there. And you're going to see this a lot, especially when you get to the GMT SATCOM side of the house. You're going to see where you have all of these users that are producing these different outputs and signaling formats, running it through what's called a multiplexer, which is nothing more than a big switch based off of time. So everybody gets a piece of that time to send their information out. It's going to be in one data stream to the modem. The modem is going to take that data stream and modulate it and send it out over the airways. In receive, it's just going to take it in, it's going to demodulate it, it's going to bring it into a digital signal, have a single bit stream to the multiplexer. The multiplexer is going to use all that time and divvy out all the information to all of its users. That's basically what this particular scenario is of the elements of digital comm. And I'm only just touching just the very basics of this because this can get quite complex quick. So here's some digital terms that we're looking at. We got the binary digit. There's going to be bit versus byte. You got multiplexing, sampling, frame, non-information bits, and bandwidth. Those are some terms that you need to be familiar with. Bit, it's either a 1 or 0. Multiplexing means that you're taking all those 1s and 0s and you're dividing it up into time, making it into, let's say you got 24 users. You're taking all that information they're sending you, and you got to divvy up each one that's going to be in time and making one signal out, and you're streaming it. Sampling is where you're trying to take a portion of that to build what's called the aggregate. Aggregate is what we call mission bit stream, which is also called the data stream. It's basically the output of a multiplexer or the input of a multiplexer. Not to be confused with the users. Then you have frames. Frames are going from how many channels that you have in the multiplexer, going from 1 through 24. So a frame would be 1 through 24. Non-information bits are what's added to the 8-bit word. Things like stop and start bits. They're not part of that information, but it's needed in order to put that information in its proper slot and tell the distant end what it needs to do. Bandwidth, normally that's bits per second. It can get quite up there at times. The next thing we look at is types of multiplexing. There's frequency and time. Frequency means just what it says. It's all about the frequencies. Time, it's all about the time. In other words, Frequency is I have this particular frequency and a frequency bandwidth, and everybody is using that frequency. Okay. And if you are having problems with just that frequency, you might want to get some more frequencies in order to multiplex. When you look at time, however, what they're doing is they're using basically a frequency, but they're divvying up everybody on that frequency versus, in the timing standard. So frequency for one, time for the other. When it comes right down to it, you're going to use more frequencies for passing data than you will for time. Of course, there's more to that. Things called CDMA, code, and it uses multiple frequencies in sending it over using time and codes. Crazy stuff, I know. And that's the next couple modules here, or next couple objectives. You got synchronous, asynchronous, and ISO. Synchronous meaning that you are on time all the time. I like to equate that to a train coming up the depot, right? It only has room for one boxcar. You pull it up, you have 5 seconds there for everybody to get off and 5 seconds for everybody to get on. You got, let's just say, 24 boxcars. That means that's 5 times 20, 24 boxcars. So that's a bunch, isn't it? Leave that one alone. But the bottom line is you have X amount of time to take information off or put information on. If you don't have any information to take off or put on, you lose that time. With asynchronous, and this is what computers use, especially there and I'll explain why Bingo or Boingo, whatever it is that you guys are using, has so much difficulties, is async is talking about time slots. The problem is it uses stop and start bits, which can get quite bogged down in time. So when you think about it, if no one's using that time, you get bumped up quicker and get to use that time slot, which makes everything else appear to be quicker. Even though it's using the same amount of time, if no one's using it, you get to take that slot. You get to go ahead of the crowd, so to speak. Kind of like Disney, where they use those fast passes. The async, when you compare it to Boingo, and I give you this, Boingo during the daytime from about lunchtime to probably about 6, 7 o'clock, you guys are probably having a rough time staying on Boingo. Correct me if I'm wrong. When it starts getting later in the night, things start to become a little bit easier. You can start playing your massive multiplayer games. You're not getting bumped off. Your ping rate's really good. Am I correct?
Some nights it's kind of bad.
Yeah,
It
it's
depends
probably
if there's a game releases. If there's like a game release like Call of Duty
okay.
or like a few weeks ago Cyberpunk, then
Ooh.
everybody's downloading and using the internet, so it just makes it
Yeah,
worse.
but I can guarantee you around that 1, 2 o'clock time frame, it's going to be pretty doggone easy to get on. Why? Because there's nobody else on. So you're using all of their time. Now you look at something called isochronous. Isochronous is what we call an async at a sync rate. What does that mean? It means I'm still using stop and start bits. It's pretty much information heavy on the async side, trying to find those time slots. But with that in mind, I'm doing it at a synchronous rate. Normally, ISO, there's not many uses for it nowadays. It used to be quite big back in the day. Vids was one that used to use it because they would have a lot of sensors, a lot of video that's coming through. So they would use ISO. And I also like to go with, if you're not using it, they have something called stuffing bits. Not to be confused with stuffing the turkey, with dressing. But stuffing bits is what is needed. If you don't have any information on there, it's going to use stuffing bits to make sure everybody stays in sync. So think about it. You got synchronous, asynchronous, and isochronous, or ISO. And what I like to do is to end this with ISO is I always say this little caption of, has anybody seen the movie Tron Legacy?
Yes, sir.
I'm sure
Love
a
that
couple
movie.
of you have. So what was Korra?
She was an ISO.
And where did an ISO come from?
They're like, from what I remember. Oh, you're talking about from our stand or our viewpoint, or from the movie?
From the movie.
I guess they're like intelligent, like in beings. They had their own, like they thought for themselves in a. So basically, what we're talking about now. So they thought they could think for themselves in a programmed world.
Mm-hmm. So you had games and programs which were synchronous and asynchronous, and out of it came ISO.
I just thought about that,
Yeah.
so that's pretty cool.
You see how that can relate just from a movie, and if you think about it, it applies to this. All right, next up, these are some more, or this is some more information about synchronous, talking about frame bits, staying on time. Just remember, frame bits are what keeps things in sequential order. Async, this one is all about if you're not using it, it's going to take it. But the problem you got is because it has start and stop bits, it adds to the overall uh, bandwidth. So it's going to take more time in order, let's just say everybody is on, it's going to take more time to get to you. With ISO, this one is more about I still have all the time I need, but I'm pretty much bandwidth heavy on it. Why? Because you got start bits, you got stuffing bits, you got a lot of non-information bits. So an 8-bit word could probably come with another 8 bits of information to keep it in sync. No, bye bye bye. No, bye bye, guys. I keep forgetting you didn't grow up during the boy bands, right?
I was there.
I was there.
Almost had to go watch them. Luckily, tickets are sold out. My daughter was that age.
Yes, sir.
All right, so signal formats. Just very highly did you go through these. You got non-return to zero, you got return to zero, and you got condition diphase. With non-return to zero, there's only two. However, this part right here, I have not seen a multiplexer not use it internally. NRZ is always used in multiplexers. I've not seen anything different. Okay, so that doesn't mean there isn't one out there. It just means I have never seen. I don't know of any of them, and I have done some research on these. But the biggest thing is I don't know of any other multiplexer that does not use NRZ, non-return to zero. The other thing too, this little thing, not self-clocking. What does that mean? It means that I have to send a timing signal with the format, which makes it kind of bandwidth heavy. In other words, additional information. You got return to zero. There's 4 different types to this one. You got RZ neutral and bipolar. These are not self-clocking. What does that mean? I got to send a timing signal with it. These two are self-clocking, and I don't have to send a timing signal with it, which means that I'm free to make it faster if I need to. And this one, condition diphase, is self-clocking, but it is so much more different than the other two formats, the NRZ and the RZ, all because it does not use a voltage to determine its ones and zeros. It's all about the transitions. Okay? And we go through each one of these. NRZ neutral, those are 5-volt differences. 5 volts is a logic 1, a 0 is a 0. Polar, same thing. There is the -5 to +5. -5 is a 0, +5 is a 1. The reason you can use longer cables is because the difference between 5 volts on neutral versus 10 volts on polar. So it can go farther than neutral. Again, it is not self-clocking. Now, RZ neutral, this one, again, it appears to be the same way as the NRZ. The difference is halfway through the clock cycle, if it's at a +5, it's going to come back down to 0. Whereas NRZ, the only time it's going to change is when you have another logic coming in that's different than the other logic that you were at. With RZ Polar, this one is self-clocking. Self-clocking signal format right there. That's a signaling format. Because of it, you don't need to send a timing signal. So far, everything else, you need to send a timing signal with it. This one is, you got +5 is a 1, or a -5 is a 0. Halfway through the clock cycle, you are going to go back to 0. All right, and it's easier to show you on these things, but with this particular unit objective, there's not enough time in here to do that. So we kind of give you a idea of what to look for as far as key points. With RZ bipolar and RZ bipolar with 0 suppression, the bipolar is exactly what it means. It means it flip-flops between logics of 1. It's either a +5 is a 1 or -5 is 1, but it never goes to 0. It does go to 0 when you're at the ones, but not the 0 itself. The interesting part is we always called it alternate mark inversion. Why is it called alternate mark inversion? Because it flip-flops between the two. With RZ bipolar 0 suppression, this one is self-clocking because of the amount of zeros in a row. It will throw what we call a bit violation. The bit violation will tell the distant end, hey, we got a problem here. I was supposed to have a +5, and instead it came back as the same -5 as the last one I threw. So if you are at a -5 for the first logic 1, the next logic 1 should be a +5. But because I threw a bit violation, instead of a +5, I should have, which is what should have happened, it threw a -5. And it's telling the distant end, crap, there's a problem here. I had X amount of zeros in a row, so I need to get back in time. So it syncs up. With conditioned diphase, this one doesn't care if it's at a +5 or a 0. It knows that with a logic of 1, there's only going to be 1 transition, and with a logic of 0, there's going to be 2. So what does that mean? It means that during the clock cycle, if I put in a logic of 1, if I started at 0, it'd go from 0 to 5. If I was at the 5, it would go from 5 to 0. Crazy, I know. For logic 0, it's going to transition 2 times. It's going to go from 0 to 5, 5 back down to 0. That's the way it happens in that clock cycle. Because of doing that, it's considered self-clocking. Yeah, analog to digital conversion. You've seen this before. It's called PCM, pulse code modulation. It's developed from the Nyquist theorem. Most of our PCM comes for that. Has anybody ever seen Audacity or used Audacity, the software program for audio?
Yeah, back in high school.
Yes, sir.
Okay, well, if you ever convert whatever music that you're going to do and you export it to an MP3, you will see different modes of PCM, everything from 8-bit to 320K to convert it. That's pretty good. The more you sample it, the better the quality. Of course, it requires a lot of processing speed when that happens. PCM is in 3 steps: sample, quantize, and encoding. Just remember what is done with each one of those steps. The end result is you develop an 8-bit word. Next up, you got frequency shift keying. Uses frequency. I think the higher the frequency, you get a 1. The lower frequency, you get a 0. It doesn't change until there's another different logic that comes in there. You got amplitude shift keying, same way. The difference is 1 is probably a larger amplitude than the 0. Again, it won't shift until you get a different logic in there. With phase shift keying, this one starts getting a little bit more convoluted. When you look at the phase difference, you're looking at binary, which is 1 or a 0, binary meaning 2. Quadrature, meaning that there's 4 different states, which is either a 0, 0, 0, 1, 1, 0, 1, 1. So that's 4 different cases out of 2 bits there. Quam, oh my goodness. Quam is on a different scenario. Now, with binary phase shift keying, it normally shifts either at the 0 or 180 for your logics. However, with quadrature, it's going to shift at either 0, 90, 180, or 270. So those 4 points on there versus 2 points. Now with Quam is a mixture of amplitude and the phase shift keying. So they put it in the phase shift keying because there's so much to it. You can put, in the last count I saw, that they don't have too much problems with is 268 different logic states in 4 different quadrants. Yeah, research that one and watch your mind blow up on it. The biggest thing is this is what everybody is going to. This is what communication, we're talking everything from your servers, your modems, your radios, all using Quam because you can pack a ton of information on. How else do you think we're going to get to 4K and 10K TVs? So we've gone through digital communications and the necessity of digitization, elements of digital comm terms, types of multiplexing. Mind blown, no doubt. I would say so. All right.